Okay, so we're going to talk about limiting an excess reactant. I want to remind you of just the definition of limiting an excess reactant. Remember we said that in a reaction, one reactant will always run out first. Well, typically will run out first. The limiting reactant is what we call that reactant. It limits how much product we can form. So in other words, it's in charge of the maximum amount of product you can make. It controls how much you can make. The excess reactant is exactly what it sounds like. It's going to be in excess. There will be some of it left over. So in class today, we looked at sort of a silly example of a recipe, and we related that to a chemical reaction. So the recipe we talked about had to do with making a peanut butter banana sandwich. We said to make one sandwich, you needed 2 tablespoons of peanut butter, 4 slices of raisin bread, and 1 banana. And so we wrote that recipe so that it looked sort of like a chemical reaction. Note that the coefficients that we see here are similar to our mole ratio that we've learned about, or we use for the mole bridge. So again, this is just to review what we looked at in class. I said, so how do we determine our limiting reactant? Using this example, I told you that, so I went to the grocery store and I purchased some peanut butter, some bread, and some bananas. And this is how much I'd purchased of each of those items. So in order to figure out how many sandwiches I can actually make, we're going to start with each of our givens. Since we have 3 reactants, we are going to do 3 little conversions. And what you want to do is you want to convert to the same product, sandwiches in this case. So we started with our givens, and we used the mole ratio from the balanced equation to get the coefficients, or get the ratio that they each reactant is needed in order to make the one sandwich that we have here. So we determined that we can make 35 sandwiches with the peanut butter that we had purchased, 50 sandwiches if we used up all of our bread, and 40 sandwiches if we used up all of our bananas. Well, the question wanted to know who was the limiting reactant. We determined that it was the peanut butter, and what we said was, the reason we knew it was the peanut butter is because it made the least amount. It's going to run out first. The peanut butter was the limiting reactant. That means that the other 2 reactants are the excess reactants, the raisin bread and the bananas, or the excess. To answer the last part of the question, how many sandwiches can we make? We could only make 35 sandwiches. So the way you identify your limiting reactant, once you converted to the same product, whichever one that makes the least amount is your limiting reactant, and that's how many sandwiches we could make here, 35. So that's sort of a simple example that we can refer back to. If you ever get stuck, think back to this example. Another place you want to look to in case you maybe get stuck is to this slide of the notes. So we already looked at the steps to determining your limiting and your excess reactant. What we're going to do to make this simple is I've given you 3 little steps here to follow. When you're asked to determine who the limiting and the excess reactants are, what you want to do first of all is you want to convert each reactant to moles of the same product. Like in our peanut butter banana sandwich example, we went to sandwiches. If you happen to have more than one product, I want us to always use the first product that's written in the chemical equation. That way everyone always has the same answer. Once you convert to moles of the same product, you're going to compare your answers. Just like here, we compared our answers to how many sandwiches we could make. So here we said the 35 sandwiches to let us know that that's the most we could make because our peanut butter was going to run out. So when you compare your answers, the reactant that produced the least amount of that product is your limiting reactant. It is the thing that controls how much product you can make in the reaction. All other reactants are considered in excess, and so we call those the excess reactants. And you can abbreviate excess reactants with an X and an S, or you can just put ER for excess reactant if you would rather. So let's look at a couple of examples that are from your notes, some actual chemical reactions. All right, so the first thing you want to do is balance your chemical equation. And so this one is not balanced. And to balance it, you need a 1, 4, 1, 2. So balance your equations first. So this problem says if 2 grams of HF is combined with 4.5 grams of SiO2, which is the limiting reactant and which is the excess reactant. All right, so what we're going to do is we're going to take our reactants and convert them to moles of the first product. Again, if you get stuck, go back to the slide in the notes. It tells you exactly what to do. Convert the moles of the first product. We're going to go to the first product written. Now, of course, you could go to grams of the first product, but that's going to just be a longer conversion. I'm trying to show y'all the fastest way to get your answers. So we're going to start off with 2.0 grams of HF. And we're going to start off with 4.5 grams of SiO2. Now, keep in mind, these are like our ingredients. In the peanut butter banana sandwich example, we had 3 ingredients. So notice we did 3 little conversions because we had 3 reactants, if you will. Well, here we have only 2 reactants. Look up here, only 2 reactants. So we have 2 little conversions we're going to do. Now, we're going to always go to moles of the first product. So this is my first product. So we're going to go to moles of SiF4. Now, of course, if you wanted to go to grams, like I said, you can. But it's going to make this a 3-step problem because gram to gram is 3 steps. This grams to moles is just a 2-step problem. So we've learned how to do the 1-step mole to mole problems, the 2-step gram to mole problems, and the 3-step gram to gram problems. This one is a gram to mole problem. So that means we need to get our units to cancel. We first need grams of HF to cancel here, and that means this is the molar mass. So you need to calculate the molar mass of HF. Now, just for time's sake, I'm going to go ahead and tell you what it is. If you want to pause the video and calculate it yourself, then that's fine. But I'm going to go ahead for time's sake and fill that number in, 20.01 grams per mole. Now I need moles of HF to cancel, moles of silicon tetrafluoride on top. And this is our mole bridge. So these numbers come from the balanced equation. Up here beside of the silicon tetrafluoride, there's a 1, and the HF has a 4. So this is going to allow us to convert to moles of SiF4. And when you plug that in your calculator, you need to round that to 2 sig figs. So remember, leading zeros do not count. 0.025 moles. Doing the same thing with the other reactant. So we need grams of silicon dioxide on bottom, 1 mole of silicon dioxide on top. Find the molar mass of silicon dioxide, you'll get 60.09. Again, I'm going to work through these pretty quickly because there's only a 10-minute limit on this video. So if you wanted to pause the video, you certainly can. If you want to calculate the molar mass on your own, just to make sure you understand how to do that. The mole bridge numbers come from the balanced equation. It is a 1-to-1 ratio. So when you plug this into your calculator, you've converted to moles of silicon tetrafluoride. That you find that we can make 0.075 moles of the silicon tetrafluoride. Now, this is the point where you can decide who the limiting reactant is. Remember, whichever one makes the least amount is your limiting reactant. Reactant that produces the least amount is your limiting reactant. So, the smaller number is 0.025. That means that the limiting reactant is HF, so you would write down the LR is HF, and the excess reactant is the other reactant, SiO2. And if I were to ask you how many moles of the silicon tetrafluoride can I make, you would just look up here to ever how much the limiting reactant made, because when he runs out, you cannot make any more. So you can make 0.025 moles of SiF4 if you were to be asked that. If they wanted you to tell how many grams you